Welcome, everyone, to the Intel Builders webinar program. Thank you for taking the time to join us today for our presentation titled Decoupling Storage from Compute in Apache Hadoop with Ceph. Before we get started, I wanted to point out some of the features of the BrightTalk tool that may improve your experience. There is a questions tab below your viewer. I encourage our live audience to please ask questions at any time. Our presenter will hold answering them until the end of the presentation. Below your viewing screen, you will also find an Attachments tab with additional documentation and reference materials, including a number of websites and documents mentioned in this presentation. Finally, at the end of the presentation, please take the time to provide feedback using the rating tab. We value your thoughts and will use the information to improve our future webinars. Intel Builders webinar series takes place live every week, so check the channel to see what is upcoming and access our growing library of recorded content. Today we are pleased to welcome Veda Shankar. He is the Director of Emerging Technologies for the Solution Business Department Group at Quanta Cloud Technology and has extensive experience with software-defined data center products. He is a customer-oriented IT specialist with a unique combination of experience in product development, marketing, and sales engineering. He has been part of many startup ventures in the Silicon Valley with products ranging from embedded consumer electronics platform to enterprise software. Welcome, Veda, and thank you for taking the time to join us today.
Thank you, Renee, and welcome everyone to the webinar. Today's webinar is based on a study conducted by engineers at Intel and QCT who engaged with a large service provider to solve their storage problems. The problem encountered by this cloud service provider is endemic to most Tier 2 CSPs, such as online retailers and streaming music services, who constantly face pressure to keep up with the demands of the big data age. The data footprints of many of these companies already cover many petabytes. So even at a relatively low rate of data growth, they often need to acquire hundreds of terabytes of new storage every year. At such a scale, any inefficiencies in capital expenditures and resource allocation are greatly magnified. CSPs today need to meet these storage acquisition challenges of data explosion while remaining competitive. They need to be agile, fight for differentiation, and provide value-added services that satisfy consumer demands. Now, let me do a back here. Okay. Now, most cloud service providers, as you know, use Apache Hadoop to analyze their large data sets, as running traditional queries is not very efficient. Now, unlike traditional relation database, with Hadoop, you don't have to pre-process data before storing it. You can store as much data as you want and decide how to use it later. That includes unstructured data like text, images, and video. Now, Hadoop's distributed computing model processes big data fast. The more computing nodes you use, the more processing power you have. Now, that brings us, to the first challenge. So what are the challenges that are posed in scaling the storage capacity in Hadoop? Now, because of the way that Hadoop is designed, Hadoop nodes share both processing and storage responsibilities. Data stored in Hadoop is stored in the native Hadoop distributed file system, popularly known as HDFS, on hard drives that are local to the Hadoop nodes. As a result, Hadoop storage and compute are system-bound and cannot be scaled independently. When organizations acquire more Hadoop storage, they end up purchasing compute resources that they might not need. Over time, acquiring more Hadoop storage leads to more and more compute capacity going unused. Now, this is a waste of processing cycles and IT spending. Now, this problem is especially significant at CSP scale. So the first challenge with Hadoop storage is that it is tied to the compute. Now the second challenge is that acquiring Hadoop storage is also inefficient as it can only be used for Hadoop workloads. If a company needs storage for other types of workloads, they need to purchase additional capacity dedicated to storage technologies other than HDFS. So in essence, no multi-tenancy support in Hadoop. This also means that you have to routinely be copying data in and out of HDFS from other applications. Now, for many IT decision makers, commonly, they choose to archive data in Hadoop, but storage and compute resources in Hadoop are bound together on each node, as we just mentioned. This means that when organizations acquire more Hadoop storage, they end up purchasing compute resources that they may not need. So what is the solution for this problem where storage capacity and compute capacity cannot be scaled independently in Hadoop? Now, this problem is true if you use the native Hadoop storage, HDFS, which is based on locally attached disks. But what if you were to replace the native Hadoop storage with another storage solution like Ceph? Now, the solution we will discuss today uses Ceph as a backend store for HDFS and then optimizing performance by using performance-enhancing Intel technologies. Now, Ceph is a free, open source storage solution with a very active community that runs on commodity hardware. It is highly scalable and supports all data types. Now, using Ceph as a backend replacement for Hadoop storage can break apart the Hadoop compute and storage capacity. And then by using Intel technologies such as Intel Cache Acceleration Software and non-volatile memory express, also known as NVMe, Intel SSD drives, you can design the solution to function with very strong performance. Now, optimizing performance with these technologies can help resolve the input-output bottlenecks and provide better customer SLA support. Now, this entire solution would allow firms to scale Hadoop storage and compute independently, improving the efficiency of IT and increasing the organizational agility. It would also create a unified storage solution for all enterprise needs. Now, Ceph is an open source software platform designed to provide a unified scale-out storage solution on commodity hardware for object, block, and file-based data. Now, Ceph is open source without the premium of software licensing, and it can therefore provide a cost-effective storage solution that can support many different workloads and applications. As Ceph adoption increases in the enterprise market, more companies are looking to Ceph as a potential alternative to direct attached storage for Hadoop. Now, this solution can fulfill the promise of scaling storage and compute independently in Hadoop and allow companies to grow in a cost-effective, efficient manner. So let's look at the Ceph storage architecture. The core idea of Ceph is to provide a distributed storage system that is massively scalable with high performance and no single point of failure. It's been designed to scale to exabyte of data and runs on general purpose commodity hardware. Now, at the core of Ceph architecture is RADOS, which stands for Reliable Autonomic Distributed Object Store, and is the foundation of the Ceph storage cluster. Everything in Ceph is stored in the form of objects, and the RADOS object store is responsible for storing these objects, irrespective of their data types. The RADOS layer actually makes sure that data always remains consistent. Now, to do this, it performs data replication, failure detection and recovery, as well as data migration and rebalancing across the cluster nodes. librados is the library that sits on top of RADOS and provides access to the objects. And there are bindings in several languages like PHP, Ruby, Java, Python, C, and C++. Now, you have different interfaces that make use of librados to provide different access methodologies. The first one is the RADOS Gateway, RGW, which provides object access. So it provides RESTful APIs with interfaces that are compatible with Amazon S3 and OpenStack Swift. The RBD is the RADOS block device, and it provides persistent block storage, which is thin provisioned, resizable, and stores data striped across multiple OSDs. So this way you get performance. And finally, to provide file access, we have the Ceph FS, which is a POSIX-compliant file system that uses the Ceph storage cluster to store user data on a file system. Now, all these three talk to librados to finally access the objects that are in RADOS. Okay, now the other technology that we use to improve the performance is the Intel CAS. Now, because when we separate storage from compute over Ethernet with a solution like Ceph, there's going to be performance bottleneck, especially for demanding workloads like Hadoop. Now, we resolve this bottleneck with Intel's NVMe SSDs and cache acceleration software. Now, the Intel CAS accelerates Linux application by caching active data to local flash device inside the servers. Now, Intel CAS implements caching at the server level using local high-performance SSD media as the cache drive within the application server. So it improves both the throughput and also reduces the latency. Now, the Intel cache acceleration software installs into the Linux operating system as a kernel module. Because of the way it integrates with the OS, it is transparent to the users and the application. So there is no storage migration or application changes that are required. So now let's look at the different modes and how you can configure the Intel CAS. On the left, you have the write-through mode. Here, data is read from the backend storage and copied to the cache on SSD. Now, further reads will promote the data to system memory, and subsequent reads of cache data are returned, therefore, at very high performance at basically SSD speeds or maybe even DRAM speeds. Now, for writing, all data is written synchronously to the backend storage and also to the cache. On the right side, you see the write-back mode. Now, in the write-back mode, the data again is read from the backend storage and copied to the cache on SSD. again, the further reads may promote the data to the system memory, and so this leads to subsequent reads of cache data. Basically, you get either DRAM speed or SSD speed. Again, all writes in this case go to the cache first, and then the dirty data is written opportunistically, to the backend storage, to the HDDs. Intel cache actually provides the ability to selectively cache I/O and prioritize eviction. In this particular POC, we use the Quanta Cloud Technology QCT servers, for both compute, for storage, and also the switches. They're all QCT products, and we use the Intel, Xeon processors, the Intel NVMe solid-state drives, and of course the cache acceleration software from Intel. And we will dive deeper into how we make use of the NVMe in this particular architecture. Let's go to the next slide. So as you can see, each storage node has two NVMe SSDs that serve dual purpose. One as Ceph journal, and the other as Intel cache acceleration software. So the Ceph journal helps in improving the small write performance and also provides consistency by enabling atomic updates to an object. Now, only a small portion of the NVMe is required for each OSD drive. This is around 40 gigabytes per drive. So the rest of the space is actually allocated for the Intel cache. Now, if you look at the layout, we actually interleave the cache and the journal function between the drives in order to fully utilize the PCI bandwidth. So you will see that the drives are actually half of it is used for the Ceph journal, while the other half is used for the cache. And so this gives us the best performance. We tried in different modes by fully allocating it only for journal or only for cache, but the interleaving actually gave us the best performance result. Sorry, I'm having a problem changing the slide. Okay, as you can see here, we have basically this is the full rack layout. It's in two racks in the Quanta Solution Center in San Jose, and you can see that at the top we have the Quanta switches, and you have the next you have the Quanta Grid D51B. Actually, the next you have the QuantaPlex T41S 2U servers. These are like 4 compute nodes in one chassis, and they serve as the Hadoop, the nodes. And so, in addition to that, you basically have both the name nodes are also hosted there. Then you come to the Quanta Grid D51B 1Us. So there are 3 of them. These are 1U servers that we use as the Ceph monitors. The other servers that are there, the bottom 8 of them, They are the D51B2Us with JBODs with 24 drives. So they are used as the Ceph OSD nodes. This configuration was set up primarily to reflect this particular solution, the cloud service provider's environment, and to duplicate the exact layout that they have in their labs. Now, if you go to the next slide, you'll actually see all the different the CPUs that we are using for the Hadoop data nodes. The Xeon E5 2690s were used, and the Ceph storage nodes, we use the E5 2680s V3s, and for the monitors, we use the Xeon E5 2620 V3. Now, the exact configuration is produced here for your reference. Now, let's look at the next slide. Okay. Now, as you can see from the right side, you have the chart which actually shows the execution time of the benchmark. So we ran the TerraSort and TerraValidate. These are very popular Hadoop benchmarks. And the y-axis actually shows the execution time. So the shorter the bar, the better it is. And the yellow one, the yellow bar actually indicates the baseline. Here we use Ceph as a backend store, but without enabling the Intel cache acceleration software. And the blue line indicates with the Intel cache basically being in front of the Ceph OSDs. Now, as you can see, we got almost like a 60% improvement on TerraSort and TerraValidate. So a huge performance improvement, with using the Intel CAS. And this actually helped the customer meet the SLAs. Okay, so what are the benefits of the solution? So disaggregating Hadoop compute and storage allows enterprises to scale these resources independently and to improve the overall operational efficiency. And because it is a multi-tenant solution, we're able to reduce the IT spending. So, for example, the solution allows compute servers to be virtualized because it is independent of the storage to provide faster deployment, enhance security, and also multi-tenancy. Now, another important benefit is that through Ceph, the solution provides a single unified storage solution that meets all the enterprise storage needs. And also with technologies like the Intel CAS, we are able to deliver very strong performance to meet customer demands and ensure that the solution is able to meet the SLAs in a challenging big data environment. Now, what's next? Sorry for the little lag between the different slides because it takes me time also to see the refresh. So as we move forward, with the next phase of the testing, we want to kind of go from this very specific proof of concept to a solution that is best in its class to address this problem across the industry. And also what we want to use is we want to use our throughput optimized configuration. So at Quanta, we have actually done extensive testing with Ceph storage using our different storage optimized servers, and we have come with SKUs which are specifically suitable for throughput optimized workloads. And so we'll be testing with our S2P model, which actually is a much more denser server. So it provides 70 hard drives in a 4U chassis with 4 NVMe SSDs. And the 70 drives are actually split into as two separate compute nodes, as two nodes. So basically you'll have two Ceph nodes in a 4U. These servers also provide 40 gigs NICs, so this will really help also with the performance. Now, in addition to testing with the community-based Ceph, we'll also be further testing it with the Red Hat Ceph storage. So this will kind of address a much broader, spectrum of the user community. Next, let's look at the different QCT storage solutions that we have. We call them as the QX Store line of products, and okay, and as you can see, we have different storage servers, 1U based, all flash based, and also for more denser and capacity based models, we also have a 4U server. And what we have done is primarily divide these workloads based on whether it's a throughput optimized or is it cost capacity optimized. And we used our QuantaPlex T21P 4U box and also the QuantaGrid D51PH 1U box. Now, in the throughput optimized configurations, basically our criteria was highest overall performance, but conscious of the cost of that performance. And also, as we look for configuration that offer the lowest cost per unit of performance, we also are very conscious of the OpEx that can be, a big part of the TCO. So we kind of look for configurations that offer the highest performance per unit of power consumption. And finally, in our design consideration, we also need to make sure that we have the minimum server fault domain, and taking that into consideration, we make sure that one server does not represent more than 10% of the cluster capacity. Now, the other classification or criteria for selecting the server configuration is the cost capacity optimized. Now, here, the overall cost per terabyte of usable capacity is the driving factor. Also means lowest power and cooling cost per usable terabyte. Now, because some of the data center costs are calculated also by floor space, we also look for configurations that offer highest usable terabytes per rack unit. Now, in case of cost capacity optimized, we kind of have the minimum server fault domain recommendation actually is a little more relaxed. It's like one server should not represent more than 15% of the cluster capacity. Now, based on all these recommendations, what we have is we have SKUs specific for the Ceph storage for different sizes, like for the entry level of 100 terabytes, for like 500 terabytes and 1 petabyte and greater than 2 petabytes. And again, you have basically a 2x2 kind of a matrix with throughput optimized, cost capacity optimized. Of course, we have an all-flash SKU specifically for IOPS optimized. Now, using the same server models, we also have a similar recommendation for Red Hat Gluster storage configuration, where we have throughput optimized. Now, in addition to here, it's also classified based on whether, because a cluster is a file store, whether it's for small file or for large file performance. And again, cost capacity optimized. So we have finally, we have some links that you can go visit both on the Intel and the QCT site to learn more about the solution. And so, Renee, looks like we have a few questions from the audience. Could you please go ahead and read it?
Sure. Thank you, Veda, for that wonderful presentation. The first question I have is, don't you lose data locality with Hadoop then since you are not using DAS?
Yeah, so even though traditionally Hadoop preferred to use locally attached storage for a node manager because they want to execute the Hadoop compute operation on the same node that has the data chunk it is working on. Now, this was critical when the network speed was the weakest link. As the network speeds have become so much faster, and a lot of the Hadoop consumption is relying on local memory, the coupling of data and compute to the same node becomes less critical. Now, this decoupling actually allows for scaling both compute and storage independently, which is what we saw with Ceph as the backend. Also, like storing Hadoop data in columnar format also allows for compression and hence lesser data transfer over the network. So again, all these driving factors have made this dependence of data being co-located with compute less critical.
Thank you. The next question is the Ceph storage servers all tied up only using Hadoop? Can I use the storage capacity for other applications?
With Ceph, actually, you have this concept of pools. These are logical partitions, to store objects. As we mentioned, everything is an object, but you have actually a Ceph pool where you can carve out, basically the pool holds a different number of placement groups, and now which in turn, holds a different number of objects, and now these objects get mapped to the OSDs across the cluster. Now, every single pool is actually distributed across the cluster nodes, and hence, you get basically the resilience. Now, the advantage is now you can create pools with different performance criteria, And so you can actually create a pool with two-way replication or three-way replication. You can also create erasure-coded pools if it is mostly for archival. Also using the crush maps in Ceph, you can actually have pools which are SSD only, so highly performant, or you can have a mix of hybrid, with both SSD and HDD. So it gives you a lot of flexibility where you can take your Ceph storage servers, carve out different pools for different applications, and definitely, the Hadoop is one of them, but you can always have multiple tenants.
Thank you. How much NVMe capacity is needed to benefit from this solution?
Actually, if you notice from our one of our slides that we are interleaving our NVMEs for both the journals as well as the Ceph journal as well as the Intel cache acceleration software. Now, and the Ceph journal itself only consumes about 40 gigabytes per OSD drive. Now, the basic, the default mode with Intel cache is it caches everything, right? But with the version 3.0 of the Intel cache, there's a feature called I/O classification. Now, this we basically exploit this feature, for improving the Ceph performance by only caching the Linux metadata, or basically the inodes, and this, in particular for the Hadoop workload, it improves the performance a lot and has the most, I would say, impact. So you're caching much less than the whole, amount of data that is going through Ceph. So you need about 5% of or less of SSD cache size of the total backend data store on each Ceph OSD server.
We have two more questions. Which Linux distribution providers support for HDFS via Ceph?
Actually, Ceph is supported on both, Red Hat Enterprise Linux as well as on Ubuntu. So you could also deploy it on CentOS. So you have the choice of going with any one of those, Linux distributions.
Thank you. And the last question I have is, do you have storage performance numbers that you measured with the Ceph cluster configured with the two NVMe drives acting as cache journal?
How much storage performance did you measure? You have storage performance number that you measured with Ceph cluster configured with two. Yes. So all the performance numbers that you see on the deck are based on the two NVMe drives on each storage node, and they're shared by 24 drives, which are all your HDD 7.2 kRPM drives. And we are using the Intel P3700 NVMe SSD.
Thank you, Veda. That is all the questions we have today. I'd like to thank you for your time and taking the time to provide us this wonderful presentation. And I would like to thank the audience for attending as well. So I hope everybody has a nice day.
Yeah, thank you very much for attending the webinar. Have a great day. Bye-bye.